Hello, my name is Eimly Krull, and today I'm going to be talking about the ZetaCompact and Zeta potential. First, I'd like to give you some background information on colloids. Colloids are suspension of particles in a solution. These particles can range anywhere from 1 to 1,000 nanometers. The most common form of colloids is a sol, which is solid particles suspended in a liquid. However, there are also emulsions, which are liquids suspended in liquids, and foams, which have gas particles dispersed in either a solid or a liquid. Lastly, there are aerosols, which are solids or liquids in a gas. Today we'll be focusing on the sol colloid. A colloid is considered stable if the particles remain suspended in solution and maintain an even dispersion. If the colloid is not stable, either aggregation or sedimentation will occur. Sedimentation is simply when the particles drop out of suspension and settle at the bottom of a container. Aggregation occurs typically due to Brownian motion, which is the random migration of particles due to the collisions with the solvent molecules. Brownian motion brings these particles together, and the aggregation occurs when the particles collide and actually stick together. There are many factors that can affect colloids and determine whether or not they are stable. This includes the concentration and size of the particles in the colloid, the presence of electrolytes in the colloid, the temperature and the pH, the application of shear forces, and electrostatic interactions, which includes the zeta potential. When you have electrostatic interactions, a charged particle can attract opposite charges from the surrounding solution to it. These charges balance out each other and help maintain the neutrality. The attracted charges will surround the particles in the form of a double layer. The innermost layer is tightly bound to the particle and is known as the stern layer. The outer layer is where the charges are not as strongly associated and is known as the diffuse layer. The zeta potential is the electrostatic potential at the outer boundary of this diffuse layer. Now this double layer form is very important, and we will be discussing how it affects the zeta potential calculations later on in this video. The zeta potential plays a huge role in the stability of a colloid. Earlier we had talked about how Brownian motion causes particles in a colloid to aggregate. Well, the zeta potential works to counteract these effects of Brownian motion. If the zeta potential is large enough, meaning that the particles at the outer boundary of the diffuse layer have a large enough charge, then the particles can repel each other. This keeps the particles from coagulating and allows the colloid to remain stable. How do we measure the zeta potential? One popular way is electrophoresis. During electrophoresis, an electric field is generated between two electrodes. When the electric field is applied, negatively charged particles travel toward the anode, and the positively charged particles will travel toward the cathode. By tracking this motion, we can find the zeta potential, because the zeta potential is directly related to the direction and velocity of this movement. The ZetaCompact uses this idea of electrophoresis to measure the zeta potential. In this image, you can see the electrodes that generate the electric field, which spans across the measuring cell. The particles in the colloid can move through this solution towards either of these electrodes in the measuring cell. In order to track the motion, the particles are illuminated by a laser and then imaged by the camera mounted at the measuring cell. This is a quick video clip of silica particles that are suspended in ultrapure water. You can see the motion of the particles due to the applied electric field. To the right is an image of the path of the motion of several particles tracked by the ZetaCompact. Once the data has been collected, the mobility of the particles, seen in the bar graph to the left, is used to calculate the zeta potential based off several parameters. Depending on the nature of the particles in colloid, different equations can be applied to calculate the zeta potential. The ZetaCompact offers a fixed equation for routine colloid measurement and can also be used as a base point when analyzing unknown samples. Otherwise, one would choose an equation based on the size of the double layer that we had mentioned earlier. For very large double layers, meaning that the particles have a very large electrostatic force around it, it is suggested to use the Helmholtz-Schmoltz-Lukowski's equation. On the other hand, if the particles have a very small double layer, the Huckel equation can be used. Should the particles have a moderately sized double layer, then the Henry equation should be best. Lastly, the O'Brien equation should be used when there is a significant effect due to the relaxation time. Double layer relaxation is simply the redistribution of charged species in the system as it seeks a new equilibrium, meaning that the repulsion of particles due to electrostatic forces is time-dependent when you apply the electric field during electrophoresis. Other things to consider when using the ZetaCompact is the limitations of the machine. This machine has the ability to measure zeta potentials from negative 150 to positive 150 millivolts, and has the conductivity of 100 microsiemens to 100 millisiemens. Furthermore, the colloid must be at room temperature above and below 40 degrees Celsius with a pH of 2 to 11. The particles must be between 0.1 and 30 microns in size in order for the ZetaCompact to be able to track the motion, and at a concentration of 10 to the 6th to 10 to the 9th particles per centimeter squared. When preparing samples for the ZetaCompact, there are a few key aspects to consider. Perhaps the most important is the particle concentration. If there are too many particles, it will be impossible to track their motion, but too few particles can lead to errors and even the inability to collect data at all. We suggest a concentration of 50 parts per million. If a dilution is necessary, it is important to keep all other factors constant. As mentioned before, the pH, temperature, and the addition of electrolytes and surfactant can affect the stability of the colloid. Therefore, make sure that the solution used for dilution has the same pH, surfactant and electrolyte concentration, and temperature as the colloid you're diluting. Otherwise, you can end up with an inaccurate data. Another thing to consider when preparing samples is the volume that is needed. A minimum of 6 milliliters is needed to fill the measuring cell of the ZetaCompact, but it is suggested that you prepare at least 15 mils for your colloid. This extra volume is typically trapped in the inlet or outlet tubes used in the ZetaCompact, or it can be used to flush the cell prior to collecting data. Thank you so much for watching, and I hope that you found this presentation informative.